It's my pleasure to introduce next speaker today, Anton Alekseev from Geneva, University of Geneva. He will speak about Moduli spaces of flat connections and free algebra.
Well, thank you very much. Well, it's a great pleasure to speak here, and I'm grateful to the organizers for an invitation to the Quantum Topology Conference. Well, I must say, probably all your apologies. I don't know to what extent my talk has something to do with quantum topology, but well, okay, at least I'll try to end these speculations about the relation to the main topic of the conference. Right, so mainly the talk is about the moduli of flat connections. And well, I briefly recall what it is, but maybe we don't go into it too deeply. So let me start with this setup. So let's say G is a compact connected Lie group, and small g is a Lie algebra of G. And let's say we fix an invariant inner product. You can think that it's a hidden form, or maybe it's not a hidden form. It doesn't matter so much. Okay, we're going to return many times today to thinking about, do we have inner product, don't we have whatever this invariant scalar product. So this will be an important object. But for now, let's say once we have this invariant inner product, we have an isomorphism of G with a dual space, and this is an isomorphism of G modules. So I'll denote it by A mapped to A sharp, so where A will be an element of dual, and this will be an element of the Lie algebra. Now, well, that's the first observation, which is obvious. The second observation, which is less obvious, is as follows. So, moduli spaces of flat connections on oriented surfaces symplectic. So, well, in the ideal world, I should probably explain in detail what are moduli spaces of flat connections and what does it mean to be symplectic. But perhaps would it be okay if I skip explaining what is symplectic, and for the moduli of flat connections, I'll treat an example instead. So, as I say, these two facts, these two things, they come from the fact that we have this fixed invariant scalar product. Once we have it, there are these two things happening. So this is easy. This is a theorem. Maybe I should say. So this is a theorem of the T and bot. No, I don't want to say closed. Of course, you can you're right. If the surface is not closed, then one should say more about it, and that's what's going to happen. But since the statement is somewhat approximative, let me leave it. So let me immediately look at an example which also addresses the concern that Volodya raised. So let's say our surface, let's choose a particular example of a surface. This will be a two-sphere, and I'll take out 3 points from the sphere, which I denote 0, 1, and infinity, like thinking of it as a copy of CP1. And let me fix 3 elements, U, V, and W, in my group. So then, the moduli of flat connections on sigma, decorated with the data of these 3 elements. So let me write a more abstract formula and then a very, very concrete formula. So the abstract formula will be form of by 1 of sigma to G modulo conjugations by G. And here I should still decorate this form, this QVW, and you will see in the next slide what this means. Now very, very concretely, what this space is. So these are triples ABC in the product CU, CV, CW, where CU is a conjugacy class of the element U is in G. So this decoration, once you have those whatever marked points or boundary components, you fix an element in your group for each of the marked points or each of the boundary components, and you associate to it its conjugacy class. Now, we don't consider arbitrary homomorphisms from pi 1 of sigma to G, but we consider homomorphisms which land in the product of conjugacy classes for these three generators. So now, just to draw one picture, so we have these 3 points, and we have these 3 generators of pi 1, which can be realized with such closed curves. And there is, of course, a relation on these 3 generators as we chose them, and so we want the product of them to be equal to 1. And we divide by the simultaneous conjugation by group G. Right. So this is one of the spaces that we'll be interested in. In principle, of course, we can consider arbitrary surfaces of arbitrary genus with arbitrary number of marked points, but let's for today concentrate on this particular moduli space, which is, one can say, one of the building blocks of the moduli of flat connections theory. And in particular, see, so we're looking here at this funny equation, A times B times C equal to 1, right? Looks like a very simple equation, but so we're going to talk about this equation. So in particular, what the previous blackboard say, if you have an invariant scalar product on the Lie algebra, so this space carries a canonical symplectic structure. So I'm not going to write it, but well, okay, it's some kind of business then, how to write it in a nice way, what it is. But the important thing is it is defined canonically. Now, so this is an interesting space. This space will probably play a role in various quantum topology, perhaps. But now I want to look at a simpler space. A simpler symplectic space. And in order to do that, let me fix the following data. Let me choose 3 points, alpha, beta, and gamma, in the dual to the Lie algebra. Of course, recall, we in principle can identify the Lie algebra with the dual, but let's for a moment do it this way. Let me denote the orbits of the natural coadjoint action of G on its Lie algebra, on the dual of the Lie algebra by O. So O alpha is a coadjoint orbit passing through the element alpha. And let's consider the space and not of alpha, beta, gamma. So let me also write 2 formulas. One formula for those of you who know the notion of symplectic reduction, and then there will be a very concrete formula that will be understandable for everybody. So in terms of symplectic reduction, we take a triple product of 3 coadjoint orbits, And we consider a symplectic quotient by the action of the group G. Now, what it means more concretely, so one should take the triple elements, A, B, C, in this triple product. And impose the condition that A plus B plus C is equal to 0. And then divided by the simultaneous coadjoint action on all three factors. So it turns out that this space is also canonically symplectic. So here is it. Here is a canonical symplectic form. So this comes more or less from the theory of reduction and from the fact that the coadjoint orbits are canonically symplectic due to the works of Kirillov, Constant, and Surya. So this is a kind of much easier. This is an easier space. And one thing which is already obvious, here we're looking at a simple equation, but some kind of multiplicative equation. A times B times C is equal to 1. Here, if we forget about all this symplectic story, we are looking at the equation which is additive. A plus B plus C is equal to 0, right? Clearly, these are analogous equations. This is just a multiplicative and perhaps non-abelian version of the abelian equation that we have here. And one thing that we want to discuss today is the relation between these two equations. Sounds a bit simplistic, right? But that's the question that we wanted to address. How to relate solutions to the equation A plus B plus C equal to 0 to solutions of the equation A times B times C equal to 1. Let me cite a theorem which relates these two spaces. So the theorem due to Lisa Jeffrey. So this theorem says the following. So alpha, beta, gamma, small, whatever it means, because we don't need to make it too precise. We have the following statement. The moduli space is sigma, where as elements u, v, and w, we take exponentials of the guys which represent our elements in the Lie algebra, right? Remember, we can, since we identify the Lie algebra as its dual, we can send the elements of the dual to the Lie algebra itself. And these guys we can exponentiate. So these are elements of the group G. So this guy is isomorphic to F0. And this is a symplectomorphism. So in particular C, it's kind of interesting. Well, again, forgetting about symplectic structures, so this means that if alpha, beta, and gamma are small, the set of solutions to this equation can be identified with the set of solutions to this equation. And in particular, one can do it in such a way that whatever God-given natural symplectic forms, which one of them comes from the theory of reduction, and the other one comes from the Tier-Bot story, so they will exactly match. So,
does small mean near zeros?
Sorry?
Small means near zero?
Small means, yeah, let's say there is a neighborhood of 0 such that if alpha, beta, gamma belong to this neighborhood. But we'll perhaps see a little bit more, or at least we'll have means to see a little bit more in this direction. So now, what I want to do in the talk. So one thing is I want to give in some way give a formula for this symplectomorphism. And the other thing, I'll explain the relation. So you see, this looks like a problem or question in symplectic geometry of moduli spaces, symplectic geometry of coadjoint orbits. I'll explain the relation to the so-called Cashevaro-Verne problem. And this is a problem which is algebraic in nature. So we'll see there is a relation to something else, to some other field. And then probably I will end up with speculations on what to do if there is no invariant scalar product. Right, so at the moment everything is set up in the assumptions on the existence of such a scalar product. And actually, depending on timing, I wanted to show you in the end perhaps some very beautiful, beautiful part of the proofs, a beautiful part of the machine, a lemma discovered many years ago by Drinfeld, which makes it all work. So, okay, so this was a kind of setup and introduction.
So, sorry, other generalization to the case of higher genera and
sure, maybe, yeah, here perhaps, yeah, thank you for the question. In fact, let's say, so this was a theorem, I cited a theorem proof long ago by Jeffrey, and I will show you some formulas which come from my joint work with my graduate student Florian Neff. But there is in parallel a story developed by Cavazzoni and Cuno, and before them they were based on the work by Venel and Massuyo, where they actually looking at higher genera. The only thing is, see, for higher genus, it's not so okay. So here I formulate it as a global symplectomorphism. Now, if you look at the story for higher genus, then typically this space on the left will remain compact, possibly singular by compact symplectic space. But the space on the right, typically for its higher genus analog, becomes non-compact space. So they can hardly be symplectomorphic, but they can be locally symplectomorphic. So I think, if I understand correctly, so there might be like formal symplectomorphism near zero, or maybe a local symplectomorphism on some neighborhood here is symplectomorphic to some maybe like some neighborhood here is symplectomorphic to some neighborhood there. So there, okay, I don't quite know yet, but one can hardly imagine a statement, such a clean statement as I gave you here.
What about if you take genus 0 at more points?
Sure. Oh, that's.
Then this is the same.
Yeah. Then it would be this. Yeah. I mean, that's not essential. Sure, you can add as many points as you want. Once the things are small, then yeah, there would be. Again, it's just to have it more definite. It's nice to deal with 3 points, and typically it's sufficient for. But all the other cases would follow or would be similar. Yeah. Now let me dive for a short while to a very different topic, much more algebraic. So freely algebras. So let me recall that a free algebra, for instance, is 2 generators, is spanned by symbols x, y, its Lie bracket, and various multi-brackets like x, x, y, and so on, subject to skew symmetry and Jacobi identity. So the usual rules in Lie theory. In fact, perhaps for us today, it might be useful also to have drawings. So you can have drawings for elements of a free Lie algebra in terms of planar rooted trees. For instance, such a tree would correspond to a bracket of x and y, and such a tree which would correspond to this double bracket. So with obvious rules, and also you would need a diagrammatic version of skew symmetry and the Jacobi identity. In particular, there is a distinguished element in this free Lie algebra with two generators, log of ex, ey, which is the Campbell-Hausdorff series. It starts with x plus y plus one half of the bracket of x and y, and then it continues indefinitely. So strictly speaking, one should speak of a completion, of a degree completion of this Lie algebra to accommodate this element.
So you are considering algebras of field characteristics?
Yeah, all field characteristics. That's right. Now a small proposition. So there exists an automorphism of this free Lie algebra such that it verifies the following two conditions. So first condition is the generator x is mapped to its conjugate, and the generator y is also mapped to its conjugate, but possibly with some other element. So if h and g were the same element, then it would have been an inner automorphism. But now this is just an automorphism of this free Lie algebra. So g and h belong to x complete. And the second condition, f of x plus y is equal to the Campbell-Hausdorff series. Now,
So what are the quantifiers for G and H?
yeah, one can say they exist.
They exist G and H.
Yeah, they exist G and H, such that, or you can instead of saying they exist F, you can say they exist G and H, such that the automorphism F defined by this formula, because it's a free object, so you can do whatever you want with generators. So the automorphism defined by this formula verifies this property.
So they're supposed to be in some sort of infinite dimensional Lie group?
Sure, you can say, since you can introduce, maybe I should have, yeah, if I were careful, so you can introduce here gradient with a degree of x equal degree of y is equal to 1, right? So this Lie algebra is graded. Each graded component is finite dimensional. Now you can simply define by the Campbell-Hausdorff formula the group law on this graded vector space, and in this way it becomes a group. Right. Now back to this statement. You see, in the beginning I was thinking maybe I should indicate how to prove it. But then I changed my mind. You know, I like those interactive talks. Now I want to readdress the question to you. So should we have some, like, I don't know, should we have some homework in this conference? So it's kind of, yeah, it's, think about it. It's supposed to be obvious in some way, or almost obvious. So you can actually arrange things such that x gets conjugated, y gets conjugated, and the sum of two elements is mapped to the Campbell-Hausdorff series. So the Campbell-Hausdorff series is almost a sum to the leading order, but then you have higher order corrections, right? Actually an infinite tail of higher order corrections. Now, the statement is you can actually conjugate these guys such that you get the right-hand side as you want it. So let's assume that this is correct. So now let's do the following. So we'll try to define this map, right? We want this symplecomorphism. So let's try to.
I'm a little bit confused because
Sure.
ch of xy is not ch of yx.
No.
But x plus y is the same as y plus x.
Absolutely. Yes.
So
You're right.
So I think
But
I see a contradiction.
no, because G doesn't need to be like. But here I use G and here I use H.
But I'm looking at f of x plus y,
Absolutely.
which should be equal f of y plus x.
Sure, absolutely. Yes.
But
Where is the contradiction? But F, you see, F does make a distinction between, okay, x plus y is of course equal to y plus x, no doubt about it. But F, it does know who is x and who is y. You see, F, F does distinguish x and y.
This is
F
just
does whatever it likes with x, and it does whatever it likes with y. Now, of course, you can, if you exchange the arguments of G, say new G prime is G of yx, so you can, in other words, once you have an F which does that, you can easily manufacture an F which does Campbell-Hausdorff of yx. But first you need to do, one needs to start with this question. Right. Okay. So now with this F, we're trying to manufacture a map. So let me call it F hat. So a map F hat is supposed to take a triple, A, B, and C. So this triple satisfying the equation A plus B plus C is equal to 0, and it should map it to a triple ABC, which satisfies the equation ABC is equal to 1. In fact, in order to do that, I kind of first wrote a formula, but then I saw that it's actually slightly wrong. So in order to write a formula in a more convenient way, let me say I want f of Campbell-Hausdorff to be equal to x plus y. Of course, it doesn't matter so much, just the inverse automorphism. So I'm given such an f. Okay. So let me write a formula. It's not very beautiful, but a very natural one. So I take exponential, and here I take g of A sharp, D sharp, A sharp, G of A sharp, D sharp minus 1. So I basically repeat what happens here. Only I'm replacing x and y by the real elements of my D algebra. H sharp, D sharp. Yeah, sorry, I took an exponential. Somewhere there should be an exponential. And finally, I should say what happens with C. This will be exponential minus C sharp minus B sharp.
So there are too many exponentials now.
Yeah, there are two. Oh, you're right. There are too many exponentials. Yeah, and too many brackets. Yeah, so I started in a good way with the exponential, but then. Right. So this is basically inspired by this formula, and in principle, one can work out that this equation implies that the triples with A plus B plus C equal to 0 they satisfy the condition ABC equal to 1. So this is just a simple check with the definitions.
So is it indeed simple?
Sorry?
Is it indeed simple because you have J and H for A and B and now J and H for C?
No, but you see here I have G and H. They depend on X and Y, right?
Yeah.
Now instead of X, I substitute A everywhere. Maybe that's confusing. Instead of Y, I substitute B. Now I take this guy and take its exponential. It becomes a group element. I take this guy and take its exponential. It becomes a group element. I take an exponential of this equation. I get exponential of x plus y. And on the right-hand side, I get exponential x times exponential y. So it becomes like A times B is equal to C minus 1. So this equation would apply after exponentiation. So this guy will become by exponential A plus B, A times B, and this guy will become C minus 1 by exponential. So if I now put C to the right hand side, it becomes ABC equal to 1. Now theorem. And I must say I'm a little bit on purpose hiding from you the symplectic aspect of all that, but okay, now we have to rediscuss it a little bit. So it turns out that such a map is a symplectomorphism in this sense. So it, yeah, maybe I should say it here. So it descends to a map from M0 to M, and it is a symplectomorphism. The fact that it descends to a map, it's essentially the fact that this equation is mapped to that equation. Right? So we start with solutions of this equation, we end up with solutions of that equation, and dividing by the group action is automatic because all our maps are equivariant, and it turns out that it's also a symplectomorphism for free, which is a little bit surprising.
You mean that it's Poisson map or
I mean, okay, I think I formulated here in such a way that everything is symplectic.
But you mean you fix conjugacy classical of A, B, C?
Yeah, I fix, yeah, for fixed conjugacy.
But if you don't, you just get Poisson map.
Poisson map, you mean you just on the quotient space by G, right? Yeah, sure. But there it's kind of true. It's a bit trivial. It's basically saying the same. I think then it's probably easier to state it as symplectic maps. Now, maybe just for a short while, let's go back to the question. So now we have an impression that it should always work, but there was a condition for alpha, beta, and gamma to be small, right? Now, let's go back to your homework problem. Right, so here we're supposed to find this G and H, which satisfy these conditions. In principle, this G and H we're going to find as formal power series first. Right? Then the question is whether they will actually converge and give rise to some G and H which are applicable for discrete Lie algebra. So I think that's the trick, that this theorem, it's known that for big alpha and beta it's not necessarily correct. So this will fail. And that's because, at least the technical reason, because here the formal power series would stop converging. So that's why this definition would then fail for bigger alpha beta gamma.
Sorry. The proof for
Yes. Yeah.
It's a bijection.
Yeah, it's a
So
bijection.
the error might be good.
Sure.
The implication is an
Yes. Yeah.
for all ideas.
For well, was kind of if this G, right, G and H are defined as exponentials of Lie series. Now, this Lie series, if you choose them such that they converge, so I think there are some limits. You cannot extend the convergence radius indefinitely. There is some kind of limit on how
You're
good.
doing formal. You're doing formal choice here.
In the beginning, yes, but then in the end, if I want a
No,
certain
no, on that board over there.
on that board, I do formal power series.
And then it's globally defined.
Yeah, sure. Formally, it's an isomorphism. Or kind of if you think of formal manifolds, then it's an isomorphism. But I mean, if you really want to realize it,
I mean, it's an isomorphism between the triples little ABC with some 0 and the triples capital ABC with product 1.
yeah.
It's a bijection.
But again, the formal one. Formal means in reality you study some whatever neighborhood of solutions of this equation which is close to A equal B equals C equal 1. Right? That's what formal geometry kind of means. So yes, if you look at formal, so you're allowed to do only formal power series, then it's going to be an isomorphism.
Can we drop the word formal?
Sorry?
Can we drop the word formal?
Yeah, here we do. Yeah, if once, so we know that one can choose G and H with finite convergence radius, and then on some neighborhood it becomes a real kind of isomorphism in the sense that I put here. Here it's an isomorphism between whatever manifolds or maybe stratified symplectic spaces.
Sorry, and the statement itself remains true or
Remains after what?
This proof does not work if alpha, beta, and gamma are not small.
Oh, the statement fails. Yeah, that maybe, okay, we'll see, maybe we get back to it. Yeah, the statement fails. For instance, one can consider the volumes. So since these are symplectic spaces, one can compute their volumes. And the volume of this guy, in general, will be smaller than the volume of this guy. For alpha, beta, and gamma small, they are symplectomorphic, and of course their volumes coincide. But then, as alpha, beta, and gamma get bigger, the volume of this guy continues to grow, but it's not necessarily the case for this.
One more question. Are these guys non-singular for alpha, beta, and gamma small?
Oh, one can easily choose for alpha, beta, gamma generic, they're non-singular. But I mean, you can always choose alpha, beta, and gamma such that they become singular.
Even arbitrarily close to 0?
Probably, yes. I would think so. Yeah, okay, let me, then maybe we get back to this question after the talk, but probably yes. But you can always choose, like, for generic values, they will be non-singular. Okay. So, right. Now let me talk a little bit about another problem. So this is one result that I wanted to show you, but now I'll link it to another result. So relation to Kashivara-Bear. So you see Kashivara-Bear, this is a problem which comes from a different field. It comes from some kind of harmonic analysis. But the formulation of the problem will be surprisingly familiar for you. So Kashivara and Bear want to find isomorphism of the Lie algebra with two generators, which satisfies the following properties. Well, f of x is equal to gx g minus 1, f of y is equal to h y h minus 1, f of x plus y is equal to the Campbell-Hausdorff of xy. And then they want one more property. So they want one more property. Let me write it, and then let's discuss it a little bit. So they want to know something about the Jacobian of this automorphism. Of course, if I put it just like that, it doesn't make much sense, right? I have some non-commutative algebra, and I have an automorphism of a non-commutative algebra. Typically, we don't know what the Jacobian of such a map is. So, okay, let me put it in the following way. On the one hand, there is a good definition in this context, but I perhaps don't want to now speak about it. Instead, I will show you something else, which want to explain on the next blackboard what the meaning of this Jacobian. But more importantly, so this Jacobian, right, you have transformations of an object which depends on two variables. Typically, Jacobian is a function of your variables, right? When you make a coordinate transformation in, say, space Rn, the Jacobian is a function on this space. So it's going to be a function, maybe some formal function or some non-commutative function, whatever it is, of two variables. And we wanted to factorize as a product of three functions. So a function of x, function of y, and a function of the Campbell-Hausdorff series. So we want some kind of factorization property. So this comes from the harmonic analysis motivations. If this is the case, then there is some isomorphism of algebras in for the universal developing algebras of the algebra G. But okay, it doesn't matter at the moment. So that's what Kashivar and Verne wanted. Now let me explain what the Jacobian means, and let me cite one more theorem, which would sound interestingly similar to the theorem that I show you here. So to explain what the Jacobian is, so let me take this formula for the map A hat, F hat, and let me forget the third parameter. Then I had A, B, and C maps to A, B, and C. But remember, those C's in the end they are dependent, right? Small c is minus A minus B, capital C is what it is, B minus 1, A minus 1. So let me just think of it as a map from small a, small b to capital A, capital B. So this lives in the product of two parties of the Lie algebra. This lives in the product of two parties of the group, right? Now let's equip this product of two parties of the Lie algebra with the Lebesgue product Lebesgue measure. And now let's equip this guy with the product of power measures. Then all of a sudden, this becomes a map between two measured spaces. And as such, it has a Jacobian. And I suggest, for simplicity, we don't bother ourselves with the notion of this non-commutative Jacobian. Let's just think about this formula as if it were a formula for Jacobian of this map with respect to the Lebesgue measure and with respect to the Carr measure. So now the problem with Jacobian is resolved. Let me cite one more theorem. So, and this is due to Rossan and myself. So the theorem says the following. Assume that the Lie algebra G has this invariant scalar product. So then equations 1 and 2 imply equations 3. See? So, in fact, maybe just one word about the history of this Kashgar-Rubin problem. It was always known, like this problem was open for a long time, and it was always known that it's easy to solve equations 1 and 2. Right? Actually, that's your homework, I remind you. Right? The existence of solutions of equations 1 and 2, that's an easy statement. It was always considered difficult to solve equations 3, because you don't know whether general solutions of equation 1 and 2 can satisfy equations 3. It turns out that if you assume that there is an invariant scalar product, it turned out, surprisingly, that then equation 3 is automatic. All solutions of equation 3, all solutions of equation 1 and 2 satisfy equation 3. And see, that's also a similar miracle as the one that happens here. You're solving some kind of relatively easy equation in 3 Lie algebras, and it turns out it maps a plus b plus c equals 0 to abc equal to 1. That's what this equation more or less says. But then on top of it, it turns out to be symplectomorphism for some symplectic structures. And here, it turns out that it has some prescribed Jacobian under some other structures which are imposed by the Haar measure and by the Lebesgue measure.
I'm confused. So in order to talk about Haar measure and Lebesgue measure, don't you need to assume something? Like, for example, it would work if you have invariant scalar product.
No.
But in general,
no,
what do you mean by Lebesgue measure?
By Lebesgue measure on a vector space. Let's say, of course, if you want to do it over an arbitrary field, yes.
No.
But I mean, let's say over R.
You can scale it.
What is Lebesgue measure? Sure, scale it. But then, okay,
No, different scalars in different directions. So, but you cannot
for the measure.
Yeah.
There is just one scalar.
If you have rotation invariance or something. I mean, if you have some.
No, I mean, no translation. Lebesgue measure by definition, it's what? Translation invariant. No. Oh, I mean, okay, let's say, yeah, let me choose, right. Let me choose, for simplicity, let's assume it's unimodular. But no, I mean, even that, I don't think it's needed. Yeah, there would be, let's say, it's going to work for any adjoint invariant choice, and I think maybe you're right. Up to the modular character, this would always be possible. So it's okay. Let's discuss it later. But here, everything would be like more or less well defined. So there is not many parameters. There would be no worry about it. Right? Yeah. Yeah, right. No, but on a vector space, right? We have introduced arbitrary coordinate system. We have dx1, dx2 up to dxn. If you change the coordinate system, at most you get a scalar. So there is one scalar in the choice of the Lebesgue measure. So if you also say you want a left invariant Haar measure, there is also just once you decide what it is on your tangent space, you have a unique one up to a scalar. So there is not infinity of choices. Okay. So.
Excuse me, one moment. I just a little bit of G. Where enters G in your formulation? Because this.
Sure, that's a good question. Of course, that's a cheating, because I explained to you what does it mean Jacobian using Lie algebras. Now I'm using the same Lie algebras to explain to you that there is a scalar product. In fact, one can say here in the formulation of the Jacobian, one can take into account in some abstract fashion the existence of this scalar product. So one can do it in some kind of non-commutative calculus, but I just didn't want to bring it in. So okay, now see, so there is this somewhat mysterious situation. Once there is this scalar product around, many things happen. So G is equivalent to G star. There is a symplectic form on moduli spaces, and miraculously, the first two equations imply that the corresponding map has a good Jacobian and implies that it's a symplectomorphism. So now maybe one big question to which I don't know the answer is as follows. What happens if there is no scalar product? I mean, of course, one tempting answer would be that just nothing interesting happens, right? Everything disappears. However, in the case of the Kashiwara-Venn problem, it turns out that everything follows. So one can still solve the problem, but the solution of the problem becomes non-trivial. So for the part of the story, the solution now comes from the Greenfield associator theory. So one can, now not an arbitrary f satisfying 1 and 2 would solve it, but one really needs to introduce the associator. Now, the question is, and that's a question to which I have no answer, what would happen, or can one formulate a good theory of moduli spaces without this scalar product in the beginning? Because you see, the problems, after all, they do look very similar, right? That's the third equation, which is slightly different, and even the third equations, to some extent, one can relate. So I would say my question for quantum topology would be, is it possible to devise a formal theory of moduli spaces without this scalar product? And in principle, this Kashiwara-Venn example shows that it is probably much more, if such theory exists, it might be a much more meaningful and much more non-trivial theory, because after all, here this theorem, this Perosa that I cited, we call it the triviality of the Kashiwara-Venn problem for quadratic Lie algebras. Now, the Kashiwara-Venn problem for arbitrary Lie algebras is non-trivial. Now, is there something on the other side? Is there a moduli problem without scalar product? So that's the question that I would like to end up with. So that's it.
Some questions? Yeah.
So did you define psi over there? Or
C? No, I didn't. But yeah, I can. Yeah, like C is beautiful. So C of x is. Let me think, because I was switching between like formal and non-formal language. Let me write it for Lie algebras. So this is exponential of 1/2 sum dk dx pictorial place adjoint x to the power k, where dk are Bernoulli numbers.
so presumably this x is not the x. It is a generic variable, or
Okay, so then yes, right. If you want it to be like this was for the Lie algebra case. Now formally one does the following: one takes x to the k, but then one considers it not in the developing algebra, but one considers it in the space of so-called cyclic words. You know, one can, so there is a notion of cyclic words where you can commute. So like view is a cyclic word. Right, so that's the expression for psi. It It is called the Duflo function, or it first appeared in the works of Harishchandra and then Kirillov. So that's something which comes from whatever you can say, representation theory of Lie algebras or harmonic analysis.
Yeah, we have time for one question.
Can you take SL2C in the first theorem?
SL2C, okay, probably yes, but then okay, I don't quite know the following. Probably then my formula would still, it will be similar to this higher genus story. I think my spaces will be non-compact, right? And then whether my symplectomorphism would be defined everywhere, I'm not sure. I was trying to think about it, but for sure it will be valid on some neighborhood of the origin as before. Now when I go far away, it eventually may fail. So right. So at least let's say without further research, I would say it will be valid on some small neighborhood of the origin. But there it will be symplectomorphism as everything has stated.
Sure. In the last question, Sergey, please.
Yeah.
3 minutes.
In the formulation of the equivalence, you used explicitly the existence of the invariant conditional square product. When you formulated the theorem, you used explicitly the existence of the scalar product. How one can imagine the statement of the theorem?
Oh, no, the statement. Okay, then of course one has to negotiate what kind of structure, what kind of theorem this would be. I guess if one gives up a scalar product, one should probably replace symplectic structures by something weaker. Maybe like if they're inspired by the Kashin-Arrow story, this perhaps should be just measures. Right? Of course, if we have a symplectic structure, then we automatically have a little measure coming with it. Maybe like the measure survives. Okay, let's say we're now speculating and very optimistic. Maybe the measure survives and symplectic structure fails. Or right, for instance, because here, right, we still have measures. Of course, here we had a somewhat special context. The measures were a little bit God given to us, an effect measure or power measure, but. Who knows, maybe in the general case, one can also imagine something of a sort. But yes, of course, one should give up something. But maybe something, well, yeah, maybe symplectic structure. It would be a different theorem, but still, if it were possible, that would be nice.
Okay. So, according to schedule, we have no break now. We will wait for break after your talk. You have to prepare. Do you have a computer specialist?
I see a computer, but